Hi, everyone. Welcome back for another session of deep learning AI stuff. I see people are still coming and going, coming in mostly. So we'll wait another minute and then get going. In myself, I see everything's being recorded. Hopefully you can hear me and see my shared screen. Sweet, thank you. Awesome. Now this session is being recorded, so if you do come late, obviously the recording is available, so you just rewind me. So in the interest of time, I will begin. All right. Hopefully this thing still works. Yep, cool. All right, so welcome to this session, deep learning stuff. What do you do? So I'm going to make some assumptions. I'm going to assume that you have some data that you need to process. You've got some science that you need to do, or there is some sort of processing that you need to apply AI to. And so if we get started, I guess the first thing, so we can assume you have data, which should hopefully be obvious, but let's get going. But then what I'm going to talk about today is the entire pipeline of what's going to happen first. And this is why I'm doing all of this stuff. And then we're going to build the code for it. And we're going to do it in, we're going to solve a very simple computer vision problem. And then we're going to solve it using 3 different frameworks. And so you get to see this is the same for all of them. And then what changes is the semantics a little bit. And hopefully from that, you get the idea of how, no matter which framework you choose, you kind of see the interactions of what's going on. So I guess the first thing I like to think about is the data prep. What does that mean? So here you do your data splits. That means train, test, etc. Why do you do that? Well, what you want to do is in deep learning, you're going to train a model. And when you have a model, it's going to be trained. And I talked about yesterday, your training process, basically you learn weights, and we're going to talk more about it in detail. But those weights are dependent on the training data. Now, in a realistic real world scenario, your training data is a set of data, but in the real world, you're going to get more data, which your model may not have seen before. So to simulate this, you will imagine that the data that you currently have, you're going to set aside a training set, and usually like 80% maybe, and then you have a 20% test split. You can also do a validation set. So you might do like 80, 10, 10, or 60, 20, 20. You might have another test called a validation test set, a validation set. And I recommend that, but sometimes you don't have enough data. At the bare minimum, you should have these splits. And the idea is to make sure you have set it up for a realistic scenario. So the training set goes into your model, your validation set, if you have one, you use that, which is still independent from the training set, but you monitor how the training goes and you validate it. And when we talk about validation, we mean some way you have a way of measuring how good the model is. And so every step of the training, you evaluate it on the validation set and see how it's going. And then once you finish training, you're going to evaluate it, the final model on the test set. And you want to make sure, it's very important, you want to make sure the test set is independent from the training set. If for some reason you somehow mix up these two, and there are some, for example, training samples in the test set, you could have what's called data leakage, which means the model has actually seen some of the test set, and you may overinflate the validation accuracy results you get when you test your model. And a good example of that is when you train, and then when you test it, the testing accuracy is like 99 or 100%. Then you know, oh, that really should not be happening. So that's why this data split is very important. And one of the most fundamental errors that people make in deep learning is this, because in traditional machine learning, when you did these splits, they didn't really make that much difference because traditional methods wouldn't overfit that much. And now what will happen is these networks are so smart enough that they will really, really fit the data really well. So much so that when they see a test set, sometimes they don't perform very well. So that's why you need this split as well. And I'll give you a few examples of how even Google made mistakes in this, and entire neuroimaging literature made a mistake. So this is a very critical step. So Google made the mistake that they used very nice, clean, not synthetic, but clean research grade quality data in their medical imaging, or not medical imaging, but healthcare technologies. This was a few years ago. And in the lab, and even in this setting, it performed really well. Now, the problem was that the set that they had was very idealistic. When they took it into the real world, the models did not perform very well. And so the other important thing is to make sure that this data that you have is indicative of where you're going to actually use your model. The other problem that the entire neuroimaging paper and the entire neuroimaging field, hundreds of papers were found to have data leakage, because in neuroimaging there's a big data set called ADNI, or ADNI, and it's made up of ADNI1, ADNI2, and ADNI3. And what people had forgotten was that patients in ADNI1 also came back and got scanned in ADNI3, which meant that there were, and people built models out of ADNI1 and tried to use it on ADNI3. And in doing so, you have samples in your test set in your training set. And so you've got accuracies of 98% or something like that. Hundreds of those papers thrown out now, not acceptable. So very easy to do. Is validation just calculating the residuals for the validation data as a metric for goodness of fit? Calculating residuals. The last part is correct. Yes, validation is a metric for goodness of fit. Yes. Calculating residuals probably depends on what you mean by residuals. You'll see that residual in deep learning has a very specific meaning. So I'm not sure about that part. Anyway, it might make sense once I get to the residual network, the ResNet. But yes. So the validation data is a way of goodness of fit, and the test set is an indication of generalizability of your model. Okay. Anyway, I think I've gone over too much on that, but I just wanted to stress that is a very important part. You need to balance your data, although deep learning and random forests are quite good at imbalanced data. You may need to balance your data. What does that mean? It could mean you might have positive and negative samples, for example. Or in other words, you have multiple classes, but you have a total of a million samples, and there's 10 classes, and all of the other classes have 100,000 samples, except for one class which only has 100. That's an imbalance of what? 1,000? I don't know, you can work it out. But that class is imbalanced by a factor of 1,000. And that means that it has 1,000 less training samples, which means that model is not going to perform very well with that case. So your training set or your data set is imbalanced. And so you may need to balance it. You can oversample it, for example, or undersample it. So you undersample the other classes. In the example I gave, that's probably not a good idea. Or you can oversample the other class, which probably is better. You may need to, I guess, curate it. So you should check if there's blank images or there's missing data or all of that stuff. So this is pretty much all, well, I guess part of the deep learning process. And how you do this will probably determine how well your network or model is going to perform. All right. Once you got that, now you can start doing the programming part. And so the first thing you have is the data pipeline. All right. And there are a few things you need to do. You need to normalize. Normalize or standardize. A good example is zero mean unit variance. That can be easy to do if you have like vectors of data or images of data. If you have, I don't know, text data and other things, you have to look it up in the literature of how it's standardized. And the standardization is important, again, to make sure you have this generalizability. And so even your test set and your training set are put together. Without knowing a priori what the test set and the training set looks like, you are able to somehow put them on even pegging in terms of what the distribution of the data might look like. So if you're doing imaging, the histogram looks very similar. The different types of data will have different levels of balance or evenness or standardization. So you need to make sure that that's relevant to you. Otherwise, what can happen is, again, if you have a training set and you've got it standardized in one way, and then if you use a test set that's standardized in a different way, well, what can happen is the model will overfit to the training set, and then to the test set, it's actually a slightly different distribution. So in imaging, you might have a different histogram, or it might actually have a different color, or it might actually have different words in it or something. The model wouldn't have seen that, and the performance will be low, right? So you get poor generalizability. So you need to make sure it's standardized. Now, there's other things that you need to worry about. We will talk about later. You might need to regularize the data, and we'll talk about what that means. Also, we'll have to batch the data. And again, we'll talk about what that means. So, for example, in a neural network, you will not be able to take 1 million images and put it straight in to a single model. It just won't fit into memory. Hopefully you watched the seminar this morning. We talked about that GPUs have limited video memory. So you can't actually put all of the data in. So how are you going to get the data in then? It's very efficient to put it in one at a time too, right? So the idea is to batch it. And batch just basically means we're going to take a batch size, maybe 100 of them, and put 100 of the samples in at once and get 100 results and do something to that. Okay. All right. So you've got the data pipeline. The next thing is Archie, the architecture. That's a neural network, right? So being a neural network, it's kind of the shape of the or structure. You have to make sure you define that structure, and that structure itself could be research. You may have data that's never been processed in a certain way, and what network works well for that? Well, actually building this architecture that handles that data and does it accurately is actually ends up being some of the AI research. For most of you, you'll find that those architectures are already available. So you might have convolutional neural networks. You might have transformers. Transformers. So other things. You need to define the input and outputs. Right, so what might happen is you've done your data pipeline, you get something. If it's an image, for example, well, does it have color or not? What's the size of how many pixels are there? Is it 100 by 100? What is it? You're going to have to maybe even explicitly set that up. You will also have to initialize. Remember, we're doing weights, right? We need to find out the weights, but what do you start the weights at? What do you set it at the weights at? Usually we use random values, so then the fluctuations are easy to see and we can converge better. And we'll talk about optimization soon. So once you've got the architecture, then you have another important part, and that's the training procedure. Okay, and this is usually, what optimizer are you going to use? Remember we talked about that it's an optimization process. What's the loss function or the cost function? And even we're going to look at learning rate schedules. So, how are we going to adjust these things? Do we adjust these things on the fly? What do we do? Okay. And once you got that, you will probably have a model. Now you need a testing procedure. Usually this is pretty defined by the training procedure and the architecture. And so you need to check generalizability. You need to check for, I guess you want to do some validation. What else here? Overfitting. Well, I guess that goes into generalizability. And finally, and I won't be covering too much of this, you do the analysis. So, here you might look at overfitting now. Are you overfitting? You look at convergence. Can you improve it? So you got plots, etc. And there are some tools to do this. So there, with TensorFlow, you get TensorBoard. There's a website called Weights and Biases. It's a free website, but it's not open source. But they will. It's a free tool that you can use. All right. So I guess in terms of all of these things that we've talked about, one quick question for you, if you've been following so far, and hopefully you've been able to follow, is, out of all of these steps, which one do you think is the most important out of all of them? Any clues or guesses? Yeah, I may have already given it away. but yeah, it's yes, the curating the data is pretty important. But for the most part, I know you probably have to do this for most methods. In terms of deep learning, it'll probably be that one there. So you need to standardize it, regularize it, and batch it. So let's have a look at this one first. What do we mean? What do we mean by batching? Oh, we've got it. Pipeline, yes, excellent. So, traditionally, so let's call this batching. And the reason why I am really stressing the batching here is because some frameworks actually allow you to control the way things are batched. Things like Keras, for example, doesn't really care. You just tell it how big the batches are and it does its thing. In JAX, you actually need to control it, or you can control it. Again, it has other libraries or wrappers above JAX that allow you to not worry about that. But JAX itself, you do have to kind of understand some of this concepts, because then you have full control in JAX. Okay, so traditionally, oh wow, let me start that word again. So, oops. So traditionally, you might be doing a PCA or a random forest or some other processing pipeline. You have, when you have X is a data matrix, you put X, it goes straight into your RF, say, and out pops the results. And the data matrix is, and this is where the problem comes in, small. We're talking 1,000, so maybe 100 to 1,000. Well, N is 100 to 1,000, and X is a N by N matrix. So a computer could probably handle that. If you have enough memory, no problems. If you have complicated matrix applications or operations or linear algebra like SVD or something, there are tricky ways to get around this problem. But that's how you would do it. Deep learning, however, oops, my spelling's all off. So instead of X, you're gonna have to give X dash. And here's your model. Call it a model, and then you get your results. You get partial results. And here, X dash is a mini batch of the data. Right, so for example, there's a data set called ImageNet. It has 1.4 million images, and it has 1,000 classes. So this was the ultimate test back in the day. And that's about 150 gigabytes of data. All right, so and this is considered small these days. You've got open images. These are just imaging data sets. Open images, we're looking at 300 million. Right? It's around 4 terabyte. So you couldn't possibly fit it in. So what you do for ImageNet, you'd probably have a batch size of 256 images. Okay, so 256 images are fed into your neural network at a time. And therefore you get 256 outputs, classifications. And then you can average that, or you basically keep track of that. Okay, so, okay. But what does that actually mean, and how do you implement this? And the idea is now, even PyTorch supports this, something called vectorization. But what it means is if you have a function, so if you have X input to a function, gives you Y, and f of n is anything like, oops, like a network, you have this idea that you're gonna vectorize this whole process. Which is kind of like, let's say here, give you an example. X is a vector. Y is prediction. Then the term vectorize comes in is that we'll actually, so this is X1, X2, X3, sorry, these things should be the same size, X4, XB, where B is the batch size. So we feed in X0, XB, into function. Okay, so in other words, we do this. B is a function, and what we get is actually Y0, YB. Okay, so here's the cool thing. We only need to write this. And framework handles the rest. So in JAX, it's a convention now that this you would use something called a vmap. This whole process. Oops. Okay, and this is the term that you need to be familiar with. So, all right, so what we have is this thing here. Sorry, this thing here. And we just need to write this. So this might, for example, be a function that calculates something. And what you do is you design it so it just calculates given an X and it spits out a Y. And then you just say, well, I want to vmap it. And that means that you can then, this will actually give you another function. So it might be a function over here. Function equals vmap. And then when you call the function, you can actually pass in an entire data set into it. And the GPU and JAX automatically splits it across all of the threads that you have on a GPU. All right, so we're kind of getting there. So I'm sorry, if I go back, that's batching for you. That's an important part. I will see that in our code when we start the code. I'll code it after this. Okay. And in a way, I guess I thought I might talk about the GPU, but I think the only thing you need to remember is that when you do this batching, your model and your batch is then loaded onto the GPU and executed. So the difference in PyTorch is that you explicitly need to tell it that I want you to do it on the device now. And that'll be the only difference you'll see between some of these frameworks, is these little quirks and how they handle the GPU. Okay. So I'm just going to go back a little bit, go back to, oh yeah, I'm already there. And so you batch it. Now, this regularize. Okay, so at some point we've got our data. We managed to standardize it. And when we do the coding, you'll see that. We're going to take some image data. We're going to zero mean it and unit variance it. We're going to batch it. This regularization will come in when we see later. And this will end up being something like augmentation. So we'll need to augment our data. And that basically means that in some situations you might find, especially for example, images, that you might have, say, here's an entire image, but you have a cat on this side. And in the training set, all of the cats are around here, but then this cat in the test set moves over here. Now, in a visual recognition system, if the training is all done over here, there's no indication that there's a cat ever been over here. You're gonna overfit. So what you do is you augment the data by moving the cat everywhere. You can do shifts and rotations. And what that means is we're not really creating new data, but we're creating some fake data that kind of makes sure that the model sees all the possibilities. And this is regularizing the data so that it is more expectant of what the test set could be. And we'll see the first data set that we'll try coding in. It won't work it'll work fine because there's no issues of test set and train sets are very similar. But the second data set we'll see is that we get a very low performance because we haven't taken the regularization into account. All right. I know you're probably itching to do some coding now. So, but we've got to do one more thing, and that is actually two more things. We've got to look at this architecture. So in the end, we have some sort of architecture, and those are the weights between the neurons, and it's related to these, the training procedure. So the last thing we'll look at before we start coding, oops, is architecture and training. All right. So now a neural net, we remember we have these neurons and we have an input. This is a very basic neuron. That one's connected there. This one's connected there, there, and there. And this is the output. And the neurons here, so this might be I0, and here's I1. And then there's a weight 0 and a weight 1. And here you're going to have another weight, which might be, let's say, 2 and weight 3. Okay, so here we do some multiplication. And this is an artificial model of our thing, of our neuron. And the artificial neuron sort of, we have, so that's the artificial neuron. Our actual neuron, biological neuron, sort of like this. It has a bit of a core. It sort of has a little structure around it. Oops. I have no idea. Don't take my drawing too seriously. And then it has this little thing called an axon. And these are dendrites. Dendrites. So you can see our model is quite very simple. Here's the sort of real model, and the neuron, you know, takes inputs, computes weighted sums, and decides to fire. Or not. All right. So the actual architecture is, you know, the network of connections and weights. You know, in order to activate and make decisions, right? Should say non-linear, which is the really cool thing. All right. So finally, what we need to do is the training part. So this is an optimization problem. All right. And so what that means is we find the optimal set of weights. What does that mean? Okay, so that means, how do we find that? We use an optimizer, right? And what does an optimizer do? Well, if you have a loss function, so you might say loss function, loss function, right? So here is the expected output. And here is actually actual output of the network. Actual output. What we want is to minimize this. And this is, of course, task dependent. And so the loss function could actually be anything. So if it's a label, you might want to basically say it's a certain class. So we give each class a number and say it's 2 minus 2, so it should be 0. So we want to minimize that. It could be that you're trying to recover an image. So given a certain condition, you get an image. And so you compare two images pixel by pixel. You might take the mean squared error. The MSE is a good metric, reasonable metric. And you try to optimize that. And to do that, so the optimizer, this is the last bit, I promise. The optimizer basically steps in the right direction to minimize to minimize loss. And it does so by a step, size, and in deep learning, we call that the learning rate. So these are all the keywords that you're going to see in the code and we're going to start that right now. Okay, so I'm just going to go back and mark out all of the things we've covered. And hopefully we've covered everything. There's no gaps. So here's the optimizer we looked at, the cost function. We're going to look at the schedule a bit later. We've got the inputs and outputs. We've got the shape and the structure. Initialize. So what do we set these weights to? We usually set them random values. And if you think about it, that's probably the best, because what an optimizer does is it's going to twiddle all the values to see if you're going to twiddle the values in the weights to see if Y gets better or the loss function gets lower. And if it's noisy to begin with, then small changes show up quite nicely, initially quite well. The result, the instant you change something because everything else is noisy, you get a very fast change at the end. And you don't want to set it all to once, because what will happen is if you set everything to 1 and if you make small changes, it's harder to see the difference. And so you check it, set it all to random, make a little change, and then you observe everything. All right. Okay, cool. That is that. So we should not need that anymore. And now we get down to the actual coding. So let me put that aside. Do the weight sum to 1. That's probably going to be decided by, you can set all of the outputs to 1. So that's going to be the activation functions. For every layer, you can put constraints on it, so they do sum to 1. Most of the time, you probably want them to have a very normal distribution, like, so the area under the, so basically, yeah, the sum comes to 1. And we actually have layers that force it to do that sometimes. You have layer norms, we have batch norms. It really depends on the problem and what works best in the end, though. We'll see some practices, hopefully, well, maybe not today, but there are some norms that you can use to improve performance. Okay, so let me do the thing. Okay, so there's one more window there. Okay, so what I'm going to do is actually, I don't know if I can move this somewhere, because Zoom's getting in the way. There we go. What I've done is we're going to use Google Colab, because that means I can easily share this code with you. So I can just give it to you via a link, and then you can play around and try stuff yourself. So all I've done is you can do this in your Google Drive. You go to New and then More. There's a video we'll share later, but New and then More, and then you can go Google Colab Notebook and it'll fire up like this. What we're going to do is we're going to look at this data set called MNIST, which is just digits. And we're going to do a CNN classified. And I'll just put psi in front of it so I know it's a psi thing. And the good thing is it's got markdown in it. So this is a Jupyter notebook pretty much. So what I'm going to do is classify MNIST data set using CNN. Okay, cool. Then we're going to write a data block. We're going to actually, I don't know if this has been disconnected. No, it's cool. We're going to use TensorFlow. Now, the important thing you want here is we want to go change runtime type. At the moment, hopefully, am I sharing the right screen? Can you guys see that? Hopefully you can see that. Chat is quiet, so I assume you can. So one of the first things you want to check is to make sure you've got a GPU. So by default, you don't get one. You go in the hardware accelerator, and you can set it and go save. And what it'll do is it'll reconnect everything. That's why I want to do it early, so I don't have to do this later. You have a new runtime. Okay. And now I'm gonna look at TensorFlow. So the first thing is, maybe I'll add text to it. Import the libraries first in the text that I'm going to have, and I'm going to try to keep tabs of that. Yep, so that's cool. Now the thing that I want to be very careful of is what version am I using? So I'm going to run some code. Actually, maybe I should do it. Sorry. Let's do it down here. Let's see what version we get. 2.9. Okay. The reason why you always want to check the version is that things happen between versions, things break, new things get put in, default parameter values change, which can break code. So you just want to be very careful. Now, the next thing I want to do is we want to set, and to speed up this, I've already copied and pasted it. So I'm just going to copy and paste it rather than retyping everything. It's going to set some parameters. So I always like doing that. And I'll add a list of parameters here. So the first thing is, maybe I'll show you what an MNIST data set looks like. So, that's basically it. It's a black and white image. It's a 28 by 28 image. So here's a better example. Each image looks like this, and it's a digit. It's a handwritten digit. So this is a 2, obviously, and the label is 2. The goal is to load this. We have 60,000 images, roughly 10,000 of each class at least. And we try to classify by looking at the digit, what digit it is. And so the size of the image dimension is 28 by 28. We're going to use a batch size of 256. We're going to use something called an epoch. So when we train, every time we put something through the network, it's an iteration of the network. Every time we go through many iterations, until we've gone through all of the data, once we've gone through all of the data once, we call that an epoch. It may take many times over the data, many epochs, to get converged results. So in this case, we need 5. It will turn out that we'll need 5. And there is actually, there is actually 10 categories. All right. The next thing we're going to do is actually create the, now at this point, actually, before sort of architecture, we'll follow our diagram that we have, that we talked about. Next thing we want to do is probably look at the data. So let's add some text in here and say, load the data. Preprocess the data and standardize it. That's what we'll do. And we're going to use the MNIST data set. So I'm going to have to add that into our includes. We're going to use, and here's the first thing we do. We're going to use the Keras part in TensorFlow. Go back up here. And we're going to use Keras datasets MNIST. So that works fine. Not sure why that's underlined, but anyway, we're going to have our parameters. And now we've got MNIST. And what we're going to do for our CNN, this data set for MNIST does not actually have color channels. It's just black and white. And so the way the data is usually ordered is you have batch size, height, width, and number of color channels. And because this data set doesn't have color channels, we need to add it. And here we're using NumPy, which is NP. So we need to import that as well. We'll go back up, put that in there. So the good thing about Google Colab is you don't have to set up an environment. Most of this stuff is already there. And now the next consideration to do is that the labels that we're going to get, so MNIST.load data returns to us an already preset split. So for the purposes of this particular experiment, we are going to assume that the way this data set is already curated, it is already curated into tests and training sets, which is lucky for us. So MNIST already has the splits, and it has the training data, which is the images, and the labels, which is which digit it is. And this likewise for the test set. The first thing we do in this case, instead of doing zero mean unit variance, we're just going to be putting everything between 0 and 1. And the reason why this works for this data set is that it's a binary data set anyway, most part. It's fairly normalized. This will not work with the next data set that we're going to try. Okay. But this is our standardization. We add an extra dimension because remember it doesn't have color. So we just say it has one channel by using np.newAxis. And then the last thing we need to do is something called one-hot encoding. So let me write that. We use one-hot encoding of the labels. This means that we put one value, I guess like a switch, we put a one value for the index of the class. So in other words, so for example, we have 10 classes, and so you know, 2-digit would have encoding of, it's not a 0, it's not a 1, it's a 2, it's not a 3, 4, 5, 6, 7, 8, or 9. And does that like that? Yeah, that's it. And there's a function in Keras to do that. So rather than writing the function ourselves, we're just going to call that relevant function. And then we need to do it up here, like we've done with this. So we do that again. We can run all to make things easy. And there you go. So instantly, Keras gets the data set for us, which is good. It downloads it, and then it spits out the values because I've got it here. And so now we have a 28 by 28 by a single channel, 60,000 images for training and 10,000 images for testing. Okay, we've got a few questions. Good. Full screen. Oh, yes. Okay. Yeah, that's a good idea. All right. So will you please share this window in full screen? Font is really small. Oh, okay. Sorry. I should keep that up. All right. Does that work better? Hopefully that looks better. Sorry about that. If you can see the. Okay, thanks. Good. All right, so we want to add some code next. And so we've done the data. What do we have after the data? We have the architecture. So let's do that. So let's just do the text first. Now define the architecture. Warning, you are connected, you're not utilizing the GPU. Okay, yeah. That's true. We haven't done so yet. We might be hogging the GPU for no good reason. We'll get there. Now define the architecture of the classifier using convolutional neural network. And the way we're going about this is we're doing this in a not the best possible way, but we're just going to get something to work. And so the first thing is, like I said, we need to define the input, and we're going to make sure that it has a shape. And remember, n is 28, so it's a 28 by 28, or it even tells us, which is really nice, with one channel, which is up here as well. This is what we want. And again, here, we're just looking at, we're not looking at, because this is going to be about the batch size, we're not actually worried about this first dimension. It's all about the last 3 dimensions, okay? And TensorFlow and Keras use channel last, so the last dimension represents the channel. And what we're going to do is we're going to do something called a convolutional neural network and do a 3 by 3 convolution, and we need this depth parameter. It's basically the number of filters. So we're going to just define it here. We should define it up here. I usually define it up here, but just for now, we'll define it here. And this is the number of filters to learn. And so in essence, what the convolution or the conv2D does is it does a 2-dimensional convolution with a 3 by 3 kernel. It also has the activation in it, so you don't need to have a separate layer for activation. And we'll maybe do these next week. But basically all these do is try to learn a 3 by 3 filter. And then we're going to reduce the size of the image and do a 3 by 3 filter again. Because the size decreases, we're actually looking at more and more of the image. If you remember, we're trying to learn the neighborhoods, and then we learn the neighborhoods of the neighborhoods, and the neighborhoods of the neighborhoods of the neighborhoods, and so on. And so we need all of these layers. And so first we learn the neighborhood. We shrink the image using a pooling. So basically in the image on a certain window size, here 2 by 2, we keep the maximum value. So we want the maximum response. And that reduces the size by a factor of 2. So this is a 28 by 28 image here. It becomes a 14 by 14. At here, learn the neighborhood of the neighborhood, and then you become a 7 by 7. You learn the neighborhood of the neighborhood, and this actually probably have one more max pooling than we probably need. And this would probably be a 3 by 3. We flatten the 3 by 3, so you have 9 values. We connect a dense layer to it. Remember, these are just the layers we've talked about before, which is just the perceptron. We have 128 of those, and then we have the final results, which are the categories. Now we need dense, flatten, max pooling, conv, and input layers. So that's the next thing. So we got 3 questions. Good. How can we install packages in Colab and create an end? So you don't need to create an end, but you can install packages in Colab using the exclamation mark. So you go and pip. Yes, and pip. So you can go exclamation mark, pip install, whatever. Okay. Not sure about end, but we can do, yeah, there you go. Yes, thanks. Thanks, Rishi. That's good. Cool. I've just got distracted a little bit. Where was I? Oh, yes. Now I've got some text here, which I'll put in. Oh, sorry, I have to do the includes. So in the includes, I've got one line where I explicitly include each thing, but you could do it You do it by including the module and then calling each one using the namespace. So I'm just going to do that. And then I'm going to run all. So it's running each one. Right. And so what I've got, and here's the first thing about TensorFlow and even PyTorch, these are all linked together. So there's an input layer, a conv layer, a max pooling layer. And so these are all connected. So one after the other, these are all connected like this. Net2 goes into pool 2. Pool 2 goes into net3. Net3 goes into pool 3. So these are all connected together until you get output. And so you have a graph up to output, from inputs to outputs. And this is going to be important in the next step. Another question. So just okay, you're copying your code from. Yes, I am. Just so I can break it down piece by piece. It kind of looks different, does it? The mouse moving around. And so let me, so I've run that. So let me put some text in there. So that's just the explanation. But we've got output and we've got inputs. Now, what we need to do is have Keras do all of the heavy work, lifting, and create the neural network, all its connections, and initialize everything. And link that to a loss function. And in Keras, it makes all of that easy. We create a model using the model class, and then we compile it. So back here. And that's what this looks like. But to do that, we need this model. So here we are going to take the inputs and the outputs, and that's going to be our model, Keras model. And then we're going to compile it. And what that does is we assign a optimizer, a loss function, and what sort of metrics we want to keep track of. All right. Again, I'll need to import that particular line. So let me put that in. And roll again. Okay. So we're getting actually close to the end. Let me do some code there again. And what we have, we're effectively ready now to fit the data. So what Keras does is it follows scikit-learn's sort of approach to, I'll just put some text in there. So it has the scikit-learn sort of approach to model building. And so it has .fit, .predict, and .transform and all those sorts of things. So what we're going to do now is we're going to actually do the fit. And so we're going to call the fit, and the fit does xtrain. So that's the actual training data. And there's the size. We're actually going to go back and have a look at, we've called it the categorical or cat. So we're going to use y train cat. We're going to train it for 5 epochs with a batch size of 256. We do want to shuffle the input around, so that kind of helps with the generalizability. And usually you wouldn't do this, but I'm just going to take my test set as the validation data so I can immediately see how the accuracy goes on my test set. You shouldn't do this unless you're using a toy example like this. And so if I run this, it's hopefully going to go through that, and it's not going to take too long. And now it's actually building and training the model. There we go. There's the loss. The validation accuracy is 98% already. 98.8, 99. There you go, 99.09 accuracy down here. Yeah, that's our model. What do we do now? Well, what we can do is we should test it on our test set. We already were doing it with this, kind of cheating a little bit, but let's do the proper prediction. And of course, we've done the prediction. let's draw a table. And here we're going to use scikit-learn. Really, probably wouldn't do this in general in deep learning, but scikit-learn has some nice functions for this. So we can undo the one-hot coding by using the argmax. So remember, we put a 1 for where the index is the class number. So we put a 1 for the digit 2. We put a 1 where the index was 2. Now, because of that, we look at where the maximum index is, which will be 2. And that's actually our label. So this undoes the one-hot encoding. And then we use the classification report, which works out all of these cool things. And if we run that, it gives us a nice table and tells us that the accuracy is 0.99, weighted averaging and all that, recall precision and all that sort of stuff for each of the classes, which is cool. I'm just going to save that. And that's your very first deep learning model. Okay, but there's a lot of stuff hidden here. Firstly, this compile stuff. What does it actually do? I told you that it sets the optimizer and the loss function. There's some built-in loss functions here. So we're using some built-in loss function. Here we're going to use the categorical cross entropy. Cross entropy is the measure of the information that between two sets, how similar it is. And then we had a measure of accuracy. So that measures, we look at two one-hot encoded labels to see what the actual accuracy measure up, how the accuracies line up. And then it initializes everything for us. Fit also does the training loop for us. So it does a lot of the heavy lifting for us. And Keras is good if you have the data and you know what architecture you're probably going to apply. You already have an idea of a loss function, and you just want to use the standard optimizer and you just want to see what results you get. You can do this way. Okay. And what we'll do now, I think if we can do this quickly, is to show you how to do it probably the more proper way. Let's create a copy. And we're going to change this now so that we do some of these things more properly. So actually, I could have just done this instead of bouncing around two screens. Right. Here. So I'm going to remove some things here because we're going to use slightly different ones. Actually, maybe I'll just go straight into it. So we're going to use a slightly different network. We're going to use a, we're going to call this CNN. We're actually going to use a more specific network called a VGG. And we're not going to do MNIST we're not going to do MNIST. We're going to do another data set, which is a lot harder, called Sci-Fi 10. So let's change that. And we're going to import. So we're still going to use the model, actually, yeah. We're going to have to handle the timing ourselves. So we'll do that. I get the same answer for that, hopefully. Too many sessions. Okay, let's close that. Cool. Let's try that again. So we're connecting and initializing. All right, that's cool. Now our parameters are going to be different. So what are we going to look at? We're actually going to look at not the MNIST data set. We're going to look at, as I said, the CIFAR 10 data set. And here's what it kind of looks like. Okay, so you have, again, 50 or 60,000 images. You have 10 classes. Now you have colored images. And these are the 10 classes, and these are some examples of them. And it's a 32 by 32 image. So this is a more complicated problem. So we're going to need more epochs. We have 3-channel data. We end up needing 128 batch size. We're going to need more filters. And the next thing we're going to do is actually load the data set. And in this case, we're going to use a slightly different way of loading the data set. So let me explain. We're going to use a library called TensorFlow datasets. So let me just, it's called TFDS, so TensorFlow datasets. You can look it up. It has heaps of standard data sets. And the great thing about it is that this is how you use it. So you got TFDS load, give it the name, give it the split that you want. Do you want the information about it that tells you, where it came from, how many samples, etc. Do you want to shuffle the data set? And do you need to download and go true? And then you can extract the various parts of it. I think we've already executed that one. Let's execute this one. Oh, sorry, we need to execute this one first. That one, and then we execute that one. And it should download the data set and put it into our current workspace in Colab. It gets all the splits. And while it's doing that, the next stage is the data pipeline or the processing. So let it keep doing that. Let me do this stuff. Yes. So this is going to be our, oops. And actually, let that run. What we're going to do is first, we're going to remove the mean and the standard deviation of the entire data set. Now, this data set is studied so well that people have computed the mean and standard deviation. So instead of writing a script to compute the mean and standard deviation from all the 50,000 or 60,000 images, someone's done that for us. And there's one for each channel, right? Red, green, blue. The data set's set up and ready to go. And so we're going to create a function called, which is normalize, and then make sure that it's normalized between 0 and 1. And then we remove the mean and make the variance unit variance, and we copy over the label. And this stuff here is all TensorFlow datasets usage. So if you don't understand it, it's fine. Don't worry too much about it. But basically, it allows us to chain commands to process our data. So you can do it straight up in TensorFlow, or you could use a framework like this to automate everything. I will also tell you that after this, I'll also show you the PyTorch version, which looks a little nicer than this. But this is the TensorFlow version, TensorFlow datasets version. So we're going to shuffle the dataset by that many images. We're going to shuffle every image. We can map an arbitrary function to each image that's loaded. And this is what map does. We're going to then extract a batch size from that after doing the normalization. And this prefetch stuff just makes sure basically we preload all of the images from system memory, put it onto the GPU before the network and training needs it for the network. So the network is never waiting for data. So it prefetches it. I'm going to save that for the time being. And okay, So the next thing is we want to define our model. Okay. And again, you don't have to understand every part of the model. It's just a model. There we go. So we're going to use a 3x3 kernel. I've just defined it here. We're going to have an input size, which we defined up here, right? So it's going to be a 32 by 32 by 3 image input. And now we've defined it as a function. And the reason why it's good as a function is because you can put it into another file, or you can reuse it many times. It also makes things look a little bit better. And the network looks very similar to the previous one. So you have an input. It goes into a convolutional layer. We're using leaky ReLU rather than ReLU last time. We have a kernel size of 3 still. But before we actually do any downsampling, here we go. So we do a 3x3 kernel. So we do map the neighborhood. And then what we're doing is, instead of a max pooling, we're going to use a strided convolution to downsample. Now, if you don't understand that, you can replace this with max pooling. It's the same or similar. This is actually a little bit better because you learn the filter to actually do the downsampling. Anyway, so that's almost the same as max pooling there. So you downsample once, you then learn the neighborhood of the neighborhoods, you downsample again. So this is 16 by 16, this is 8 by 8, and this is 4 by 4. And then you'll keep looking at the neighborhoods. And then we do this thing called a global average pooling. So at this point, we probably have lots of 4 by 4 images. And what global average pooling in 2D does is, for all those 4 by 4 images, it just basically takes the average of all of the pixels and creates a single value for it. And you'll have that across this many times. So you basically have a long 1D array of, I guess, like a vector of averages. And then your dense, these are just the normal multi-layer perceptrons. The dense, lots of dense layers that reduce it back down to the number of classes. So basically your network is learning all of these filters that try to learn hierarchically neighborhoods of neighborhoods. It's then all pulled into a 1D vector of averages of all of those features. And then you basically learn the connections between those averages that give you a classification. We then define that as a model, as we saw before. All right. Now I'm going to add some optimization stuff. So let's go and add some text. Optimization elements. I'll just call it that for the time being, and then add some code. Right. So the next thing is, okay, so I've got on my model. What do we need? We need a loss function. And we pick one from Keras, which is, we're going to call it sparse categorical cross entropy. Notice I haven't done any of the 2 categorical here, which means our labels from the data set are not 1 and hot encoded. However, our results from our network are. And so this sparse categorical cross entropy, sparse bit says labels are assumed not to be 1 hot encoded. So then you can just use the sparse categorical cross entropy. Okay. Logits equals false because we are doing some sort of activation here. So usually you just get probability, you don't necessarily get probabilities at the end, you just get values. Logits means, have you normalized your final outputs or not? It's asking you, are the outputs from your network raw or not? And the answer is false because I'm doing an activation at the end. Okay, hopefully that makes sense. We pick the Atom optimizer. So there are many optimizers in deep learning. Atom is by far the best starting point. It's not the best optimizer, but it's the optimizer that, even with default settings, works well. So we use the Atom optimizer with a fixed learning rate, and that's its default value. And then we actually set up the network. So we call this function, we give it the input shape, which we defined earlier. We're going to use the softmax at the end. And what the softmax does is it takes the final output, which are 10 categories, and converts them into probabilities. And this is needed for one hot encoded results from our network. Okay, so this is one hot encoded, but we haven't done anything to our manual labels. All right, and I gave it a name, and you can print out the summary. So I can't remember if we ran that. No, we haven't run this, haven't we? Okay, let's see. Cool, that runs. Then we run the model, that runs. And then now we should get a printout of the summary of the model. And this is important, tells you the number of parameters we got here. We actually end up having 3.1 million parameters just for this model. Okay, I don't think we need that cell because it's different. Now, what we're going to do in this code is we're going to actually code up each and individual part. So we're not going to use the .fit, although you could do at this point, but or compile. We're going to do the individual steps that hopefully reveal to you what actually is happening underneath in deep learning. So code up the actual training procedure using gradient steps. And so the first function we're going to add is the train step. So how we're going to do the single optimization step. And in TensorFlow, you don't really need to understand too much about it, but the way you do it is you instantiate something called a gradient tape, which is basically a record of how the gradient is being computed. And what we want to do is this is our model. We want to take the images that we pass through, which is probably a batch of images. We pass it through our model, and we say we're actually training because we need to make sure that the model knows that this is the training stage. And we'll get predicted classes. And then we compute the loss. We've called that CEE loss. We compute the loss. And these two lines are almost always the same. Basically says for the tape, compute the gradient of the loss. So this is the loss. And we want to update all of the training variables in that model. And this gives us the gradient. And then given the gradients and the training variables, apply the gradients. So this is compute the gradients, so where you need to go to minimize the loss, and then apply it to the network. So all the weights are adjusted. And so all of these variables will have their weights adjusted, and you return the loss value so you can print it and do other stuff. Okay, getting there, almost there. The last thing we're going to need is some way to actually compute the accuracy. So given a set of images, run it through the model and tell me if I have labels, tell me how accurate I was. And that's all this is. So you have some model, you've got some input, it doesn't have to be a test input, some sort of images, and here's your labels. You run it through the model to get predictions. And there's a function which computes the accuracy. Again, it's sparse because the labels aren't one hot encoded, but the network outputs are. And we're saying top K, which basically means, you know, what are the direct predictions? And is our prediction that we made in the top 5? The label is in the top 5 of our predictions. And we return the both of them. So this is just to help in the training loop. Right, and now we're going to do the training loop. And the training loop looks long, but it really isn't that complicated. So let's replace this. And the training loop is just a big, well, we're going to have a function, but basically it's just a big for loop for the number of epochs that we've got, 12. We're going to just print out some stuff, normalize, initialize some stuff. And then for every batch, step the gradient and classifier and check how we're doing and accumulate those results. And we're going to print them out as we're doing it. And overall, we're going to compute the losses and how accurate we are. And we're just going to keep track of all of the losses because we can do a plot later. So some questions. What a kernel initializer is. Okay. All right. So did we have kernel initializers in this? Ah, yes, we did. So at some point, you need to initialize. So these will be your initialization of your weights. Okay. So what are you going to initialize the actual weights to? They're called kernel initializers because, you know, for a convolutional neural network, the weights are actually kernels. Okay. Now let's actually see what this says. Is it saying? So in this case, what we're trying to do is we have a truncated normal distribution. So all our weights of our network, what we can do is actually choose the type of initialization we want. And there are many types of initializations. You usually use the default ones if you're not too worried. They tend to work fine. It's when you build your own network, a new type of network, you have to be very careful sometimes. Hopefully that answers the question. Is there any other questions? Could you show us how to use TensorBoard and inspect the model? Yeah, so we're going to do that in the next support seminar next week. We're actually going to go further than that. We're going to do profiling of your model. Okay. So yeah, so that only defines our function. What we do next is actually do the, wait, let me just add a block for that. And train the model. There we go. And this is where we're just going to time it. So we're just going to call the train function and then compute the time. So let's run this. And at this point, I need to change to a GPU runtime. Oh, it's still already a GPU runtime. Interesting. And hopefully it starts running. Oh, sorry, we haven't run this block. And let's rerun that block. And then run that block. I think it takes 4 minutes to do this. All right, here we go. So you can see that the loss. So the first thing when you start training a complicated model like this, the loss should be decreasing as you're training. It should not be negative. Most times your loss function should be a positive value. Should not be negative. It should not turn into not a number. And so it should slow, well, initially, as you go through the epochs, it should reduce faster. So it's an exponential decay. And then after a while, it should plateau off. Epochs, yes. So remember, epoch is, we were going through, is an iteration of the network is going through the network once with a batch. So you take a batch, you go through the network, apply all the weights, and you get your result. That's one iteration. You have to do many iterations to go through all of the data because you only have a batch. There are a certain number of batches for your entire data. You might have, so for example, we have 50,000 images. If your batch is batch size of 1,000, then you'll have 50 iterations. After 50 iterations, you run out of data. And so you have to rerun all of the data through again. So once you've run through all of your data once, it's an epoch. And then you'll have to run through many epochs to train your network. And you can see here, it's still decreasing. So it's 1.29, 0.891, 0.58, 0.49. So even though we're going through the data multiple times, we're still converging. And this will go to 12 because I set it to 12 at the beginning. Right. Do we need to adapt code to utilize? No, that's the great thing about TensorFlow, PyTorch, and all those. So you can focus on the deep learning. You can focus in on the framework, the data pipeline, the architecture, the optimizer. Underneath, all of the implementations use CUDA for TensorFlow in this case. So TensorFlow is doing all of the transferring stuff to the GPU, threading it across the thousands of threads, computing the multiplications and all of those things for you. Without this sort of layer, it's, you know, back in the day, 20 years ago, it was a nightmare to do these things. You had to write shaders, which were per thread operations. People still write shaders, and you need to do that for games. And that's the fastest way to run things, but it's incredibly specific. Here, you can do so many things. You can build so many things. I'm using this for deep learning right now, but people use TensorFlow to do physics, to do maths, you know, to do sound analysis, engineering, and all sorts of things. And JAX, and that's why JAX is so cool, because JAX basically is NumPy, but everything underneath runs on the GPU. And so it's a general framework for science with autograd, which means you can compute gradients. And so it can do deep learning, but it can do everything else. Can we also develop the deep learning code in PyCharm? Oh, no, you can use Py. So after this, I'll show you PyTorch code, or sorry, JAX code for doing some of this. And you don't, you don't need Collab to do this. You need to set up your own environment for it on your desktop. But yeah, so here we go. So we've finished. We've got a loss function of 0.1 in the end. We've got a top one accuracy, so overall accuracy of 0.99. That seems quite a lot. What happened there? Oh, sorry. Here we go. Top 5 is going to be accurate. Top 1 is a bit too accurate, maybe. I guess that's on. Oh, sorry, that's on the test set, right? So that makes sense. What we're going to do, yeah. So that's okay. So in the training set, 0.99 accuracy is kind of expected because we're fitting, and this is where we begin to. We've definitely overfitted there because 0.99 accuracy is very high. But now we do the hard thing. We need to check how well it runs on the test set. So we load the test set now. And it's similar to loading the training set, except now we use test set. And we have testing procedure. And the testing procedure is very similar to the training procedure. We loop through all of the batches, running it through this generate and classify. But now it's the test data that's going through. So this valid DS, not our trained DS. And let's see what happens. Oh, did I just let me just make sure paste it? Yeah. So it downloads the data set. Oh no, it's done it through there. So, ooh, look at that. So it's not 0.99, it's 0.77. Our top 5 is a bit better. So our result is close. Our result is close, but it is not It's in the top 5, but the actual prediction itself is accurate 0.77 of the time. So, but for our training set, it was 0.99. So we have overfitted, right? Our network is very specific to that data for the training set, and the test set has new samples it's never seen before that don't fit as well. And so the way we fix this is what I'm going to try to do next, which was, close that. We'll be doing that. Oops. Okay. So I actually do have a collab for this, but I stress that it doesn't have to be a collab. And at the same time, we'll finish up by looking at how we're going to do this properly. What IDE do we use? I use Visual Studio Code. And if I can find it, I'll load it in my, well, I probably could find it. But there's actually a challenge. It's called the Dawn Bench Challenge. You can Google it. And the idea is, how fast can you train a ResNet for Sci-Fi 10 and get 94% accuracy at least? So we were getting 0.77, so it wasn't very good. But how do we make it good? Now we're going to look at PyTorch. So here is PyTorch, and it's got this neural networks module. It's got a functional module. It's got Torch Vision submodule, which has sort of like all the little bits for computer vision, which we're going to use for imaging. It's got transforms, and we'll use that. So the first thing we do, remember how I was saying we need to transfer all our data, and we need to tell sort of our framework where we're doing this. Are we doing it on the CPU or on the GPU? And in PyTorch, you need to be explicit. In TensorFlow, as soon as you start using tensors, it assumes you're going to go on the GPU. But in PyTorch, you have to tell it the device. So you work out what the device is. And here I'm just checking whether we actually have a CUDA device or not. We're going to set up our parameters. Here's how you use and do pre-processing in PyTorch. It's a bit cleaner than TensorFlow datasets. But basically, if you use transforms from Torch Vision, you can cascade these, you can do these things in a chain. So I'm going to convert from an image to a tensor. I'm going to normalize it, and these are the same values we use for Sci-Fi as we used before. And here we're going to do some regularization, and this is what fixes up our accuracies in the end. It's not hyperparameter tuning, it's not the model, it's actually the augmentation, the regularization of the data. We do some augmentation. We flip left, right, horizontally like this, and we do a random crop. And so we kind of look at a sub view of the data all the time. So the data is ever so different every time. Now in the test set, usually you don't do augmentation because you want it to be real and pure, basically. And so the first 2 steps are done, the last 2 steps are not done. And so we load the Sci-Fi 10. We are training. We download it. We're going to apply that particular transform for the training set, this one for the test set. We don't bother shuffling for the test set, and we define the batch size. And these are the loaders. Now, the good thing about PyTorch is that you basically do everything in classes. And initially, it may seem like that's overkill, And indeed, if you're just doing some models and some basic basic deep learning with small data sets, and you're just starting out, and Keras is a good way. But later on, you'll find that using classes like this makes things easier. And it's not too hard. All it means is that you create your own custom module, they call it. You derive from a module. You get a basic, in this case, the basic block, I've called it. You initialize it, which means these are all of the settings. So how many planes and how many in planes, so how many input dimensions, and how many, the depth of each of the convolutions. So here's the depth. And then you basically name each layer in your block, a block being a sub part of your network. You're going to chain these blocks together. And we give one each name. Here we're using batch norm to make sure that everything is normalized in between. And then we chain these together in a sequential manner. So we have a convolution layer, batch norm, convolution layer, batch norm, blah, 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 blah. The forward one is when you actually pass some data through it, what happens? And basically, we put it through each one of these, how are we actually doing this? So it actually, you do the actual chaining of these. So these are just the actual layer names and the layers, but they're not connected. And here's where you connect them together to get the final result. Now, this has the ResNet. It's outside the scope of this thing, but basically it's a combination of all these different blocks, one after the other. And you do the average pooling that we saw before. So that's the ResNet. And we define the ResNet 18 as a certain number of blocks. And that's our model. And we send the model to the graphics device. We get the model name just to be sure. And what we do is print out the number of parameters. And so this is the model itself. And it's printed out a summary. Then we define our usual cross entropy. Here we're going to use stochastic gradient descent optimizer, not Adam. As I said before, Adam is a good place to start, but to get the best results, you use a specific optimizer that you find is the best. And in this case, the other thing that helps make it really fast training and still get 94% is actually the way the learning rate changes as you train. And this is called a learning rate scheduler. And this actually makes a small difference. Instead of 93% accuracy, you can get 94% accuracy in about 1/10 of the time. So again, outside the scope of this particular meeting, course or session, but that's what we call a learning rate schedule. And then you have the training. And now in PyTorch, you don't have a dot fit. It's always gradient tape. And so this is basically gradient tape we saw before. We get for each epoch, we get a batch. We send the batch to the device. We pass it through the model. We compute the loss function, and then we apply the gradient step to the model. We print the results, and that's it. If we go through that, we'll get all these losses. And the training took, in this case, 25 minutes. But if you use a really powerful GPU, one that you get on what we saw this morning, the V100, it'll take 6 minutes. And the testing, again, similar. And guess what? You get close to 94% accuracy. All right. That's probably gone a lot longer than I was hoping for. Thanks for sticking through it. But I think you pretty much cover all of deep learning there. Now, there are things that I haven't explained, like what is a ResNet, and you can look it up. There's a nice, the original paper for it is very good. No worries. Yeah, we ended up being quite thorough, didn't we? It took a bit of time, but we went through it. The other detail is a learning rate schedule. There's so many of them. You just need to try, and that's where you would use TensorBoard and profiling, like we'll talk about next week, to work this out. So someone spent, a weekend, 3-4 hours a day just to work this out, that this is the best one that works for Sci-Fi 10 or ResNets. Yeah. And then what augmentations work best? Again, someone you sort of try a lot. And And PyTorch has many of those. All right. Look, I gotta go and pick up my kids. But I think I've covered everything. Hopefully, I know you probably have questions. Happy to get some feedback on Slack. So for the next session next week, we can cover gaps or we can cover something on the next step. Do you recommend any good book for tutorial for self-study? Yeah, so the PyTorch tutorials are good. And I'm actually going to put up a list of 3 playlists. One is for beginners, intermediate, and advanced on Slack. So go through those videos. Where do you get these codes? I'll put up the links to all 3 of these Google Collab. That's why I tried to do them here in Collab, because then I just put them on Slack and off you go. All right. Okay. Thank you very much for your attention. Yeah, hope that was useful. And yeah, we'll see you in the next one. Question, do you recommend starting with TensorFlow or PyTorch first? Yeah, you need practice. It is one of those things where you do need practice, and see if you can do the Dawn Bench challenge. Have a go at it yourself. Which should you do, TensorFlow or PyTorch first? As I said, you probably, if you're just starting out, maybe do Keras first. It's much easier. And as you build stuff and do things in Keras and you're comfortable with that, then probably either TensorFlow with the gradient tape or PyTorch is probably better. Okay. All right. Thank you very much, everyone. And catch you on Friday for the next sessions, where we'll be covering stable diffusion. And we'll start looking at different types of awesome models that are changing the way we work and study and basically everything. The next 12 months is going to be pretty amazing. But yeah, we'll talk about that on Friday. And the next of this session is next week. Okay. Thanks, everyone. Catch ya. Please.